Tonight, we're going to walk through a graveyard the size of the observable universe. You will not see headstones. There are no marked plots. There is no caretaker. The graves are scattered across 100 billion galaxies in clouds of dust and ice and rock, and the bodies, if you can call them bodies, were never made of anything we would recognize. Most of them died before they had the chance to name themselves. Some of them died before they had the chance to begin. A few of them are dying right now, on this very night, around stars whose light reaching you tonight was already a memory of an ending. The graveyard is real. The graveyard is enormous. And the most disquieting thing about it is that we are starting slowly and reluctantly to map it. Tonight we're going to ask one of the heaviest questions in modern cosmology and astrobiology, and we're going to ask it gently, with no rush, because it is not the kind of question that can be answered in a hurry. The question is this: what if life happens often and dies often, and the universe has been quietly producing and quietly extinguishing worlds in their billions for 10 billion years already? What if the great hum of evolution that gave rise to you and to me has played out in different forms on countless other worlds, only to be erased again by a runaway atmosphere, a wandering rogue planet, a nearby supernova, or simply the slow cooling of a star that was never going to last? What if the universe is not a quiet stage with one bright actor on it, but a graveyard with one survivor still standing on a single lit corner, looking out over the dark? Before we get started, sit with the proposition for a moment. It is, in its softest form, the central implication of the Fermi paradox. If the cosmos is as friendly to life as the chemistry and the planetary numbers suggest, then life should be common. If life is common, civilizations should arise. If civilizations arise, some of them should be much older than ours. If older civilizations exist, the cosmos should be loud with their signals, lit with their engineering, busy with their probes. And yet, when we listen, the cosmos is silent. The most parsimonious explanation, the one many serious thinkers now accept as the most likely, is that life arises and then dies. That the worlds are out there, in their billions, and most of them are graves. Tonight, we are going to walk through 5 different kinds of graveyards. Each one is real. Each one has been mapped, or partially mapped, by modern astronomy. Each one is full of worlds that were once candidates for life, or that hosted life briefly, or that hosted civilizations whose fingerprints we may or may not eventually find. We will start gently with the ones closest to home, and we will move outward, all the way to the most distant and the most chilling. By the end of tonight, the night sky will feel different to you. It will not feel emptier, it will feel quieter. Quieter in the way a long-abandoned cathedral is quieter than an empty room. The silence will carry the weight of what was there before. The 5 graveyards we will visit are these. The first is the graveyard of frozen worlds. Planets that were warm once, that may have held oceans once, that may have held life once, and that have since fallen into deep glacial silence. Mars is one of them. The icy moons of the outer solar system are another category. The countless rogue planets, drifting between the stars without a sun, are a third. The frozen graveyard is by sheer volume probably the largest of them all. The second is the graveyard of furnaces. Planets that became too hot to keep their water, that boiled their oceans into atmospheres, that ran away into greenhouse cascades from which no life can return. Venus is the textbook example. The hot Jupiters now common in exoplanet catalogues are another. The countless rocky worlds caught in the inner zones of their stars, slowly cooked to sterilization, are a third. The furnace graveyard is hot, and it is loud with radio noise from baked rock, but it is dead. The third is the graveyard of irradiated worlds, planets that orbit red dwarf stars, the most common stars in the cosmos, and that may have been habitable for a brief window before the stars' relentless flaring stripped their atmospheres away. The TRAPPIST-1 system, an iconic 7-planet family, may be a series of such graves. The Proxima Centauri B system, our nearest exoplanet neighbour, may be another. The irradiated graveyard is close to home, and it is filled with what astronomers call the post-habitable zone, worlds that crossed a threshold and never crossed back. The fourth is the graveyard of blast zones, planets caught in the radiation shock of nearby supernova, gamma-ray bursts, and other transient cosmic catastrophes. These are not gradual deaths. These are sudden, complete sterilizations across light-years of space. The blast zone graveyard is irregular and scattered, but it is real. Earth itself, on more than one occasion, may have passed through the edge of one of these zones, with measurable consequences in our fossil record. The fifth is the graveyard of civilizations, worlds where life arose, became intelligent, built tools and cities and cultures, and then, by accident or by inevitability, ended itself or was ended by an external event. This is the most speculative graveyard. It is also the most haunting. If the Fermi paradox is to be resolved by the Great Filter, then the filter sits somewhere in the chain of events between the rise of intelligence and the long-term survival of a technological civilization. The graveyard of civilizations is the one we cannot directly see. It is the one we're most likely to be joining. 5 graveyards. 5 kinds of death. 5 categories of worlds that may, between them, account for almost every habitable patch of cosmic real estate that has ever existed. By the end of tonight, you will have walked through each of them slowly. You will know what kills a world in each case, why we think the deaths are common, and what specific evidence has been gathered from real observations. The numbers will be precise where the science allows. The speculation will be marked as speculation where the science runs out. A small pause for shape. The cosmos is, by every solid measurement we have, about 93 billion light-years across in its observable part. It contains roughly 100 billion to 200 billion galaxies. Each of those galaxies contains, on average, 100 billion stars. Around a substantial fraction of those stars, perhaps a third or more by recent exoplanet survey estimates, orbits at least one rocky planet of roughly Earth-like size. The number of rocky planets in the observable universe is therefore, conservatively, in the range of 10 to the 22nd power. 10 followed by 22 zeros, a number so large that no human comparison helps. There are more rocky planets in the universe than there are grains of sand on every beach on Earth, multiplied by 10,000. Now consider this. If even 1% of those rocky planets ever held conditions friendly to life for any meaningful length of time, the number of life-bearing worlds in cosmic history is on the order of 10 to the 20th power. If even 1 in a million of those worlds ever produced a civilization, the number of civilizations in cosmic history is on the order of 10 to the 14th power. 100 trillion civilizations. None of them are calling us. The radio sky is silent. The infrared sky shows no Dyson swarms. The visible sky shows no obvious engineering. The cosmos appears, by every available measurement, to be either empty of intelligence or full of intelligence too quiet or too distant to detect. Slow down here. The most uncomfortable resolution of this fact is the one we're going to live with for the next several hours. The cosmos is not empty. The cosmos is full of life that has ended. The graveyard is everywhere. We are in this picture, not the first. We are not even close to the first. We are simply one of the survivors who has not yet, at this particular moment in our particular history, gone the way of the others. Expectation. We are special. Expectation. We are alone. The reality the data is increasingly pushing toward. We are late. Sit with that for a moment. The universe may be full of dead worlds, worlds that were busy with biology for hundreds of millions of years, worlds that built coral reefs and forests and oceans full of strange life, worlds that, at one point, looked up at their own night sky and asked the same question you're asking now. and then went quiet. Before we get started on the first graveyard, one more orientation. The tone of this story should not be terror. Terror is the wrong response. The right response is something closer to slow awe, the way a forest feels in autumn when you walk through the fallen leaves and feel the long memory of the trees. The cosmos is doing something similar. The leaves are everywhere. The trees are still standing in some places. The cycle has been turning for a very long time, and you are one small part of it, and your job tonight is not to grieve, but simply to look, slowly and gently, at what has come before you. Now, let's begin with the first graveyard, the frozen worlds. The first graveyard is the largest by volume of all of them. It is also the closest. You can see one of its members in the night sky with your unaided eye, on any clear night, as a small reddish dot in the constellation in which it currently sits. The dot is Mars. Mars is a grave. We do not know for certain whether anything ever lived on Mars, but we know with very high confidence that for the first 500 million years or so of its existence, Mars had liquid water on its surface, a thicker atmosphere than it has today, and a magnetic field that would have shielded its surface from the worst of the solar wind. By every chemistry textbook standard, early Mars was a habitable world. The surface was warm enough for liquid water in many regions. The atmosphere was thick enough to support weather. The chemistry of the early Martian oceans, where they existed, would have included the same kinds of organic molecules that we know preceded life on Earth. Mars may have hosted microbial life. Mars may have hosted nothing. The honest scientific answer, as of this moment, is that we do not know. We do know that the conditions were there. Then, somewhere between 3.5 and 4 billion years ago, Mars died. The death was not sudden. It was a slow strangulation. Mars is smaller than Earth, with about 1/10 of Earth's mass, and its interior cooled faster. As the interior cooled, the molten iron core that had been generating the planet's magnetic field began to freeze. The magnetic field weakened and then died. Without a magnetic field, the solar wind, the stream of charged particles flowing outward from the sun, began to strip away the upper atmosphere of Mars, ion by ion, year after year, for hundreds of millions of years. The atmosphere thinned. The greenhouse effect that had kept Mars warm dissipated. The surface temperature dropped. The water froze, sublimated, or was lost to space. Walk with me as we trace what was left behind. What was left, by the time the slow death was complete, was the Mars we see today. A thin atmosphere, less than 1% the density of Earth's. A surface temperature averaging around -80 degrees Fahrenheit. No liquid water on the surface, only ice at the poles and trapped within the subsurface. A magnetic field reduced to weak local patches frozen in ancient crustal rocks. A world that had, in its youth, been blue with possibility. A world that, in its long old age, is rust and dust and silence. Pause for a moment. Mars is not unique. The death of Mars is in fact the textbook example of a category of death that may have happened to billions of similar worlds across the cosmos. Any planet smaller than about half the mass of Earth, orbiting a sun-like star, faces the same risk. The interior cools too quickly. The magnetic field collapses. The atmosphere is stripped. The surface freezes. The window for life closes, perhaps after a few 100 million years, perhaps after 1 billion or 2. By cosmic standards, this is a brief life. A planet that lasted only 1 billion years as a habitable world has spent most of its existence as a tomb. The number of such worlds in the cosmos is enormous. Exoplanet surveys, particularly the Kepler mission and its successors, have shown that small rocky planets are extraordinarily common around small stars. The TESS mission, currently scanning the sky for transit signals, has added thousands more candidates. Estimates vary, but the count of small rocky planets in the observable universe is likely in the range of 10 to the 21st power. Most of them are small enough that, like Mars, they would have lost their atmospheres relatively early in their cosmic histories. Most of them, in this picture, are frozen graves. The frozen graveyard does not end with planets like Mars. It extends, in a quieter and stranger way, to the icy moons of the outer solar system and to a vast population of objects that float between the stars without any star at all. Walk slowly with the first idea, the icy moons. In our own solar system, Jupiter and Saturn have several large moons whose surfaces are covered in thick crusts of ice. Beneath those crusts, in at least 2 confirmed cases and possibly several more, lie liquid water oceans. Europa, around Jupiter, is the most famous example. Beneath its icy shell, perhaps 15 to 20 miles thick, there is an ocean of liquid water that is estimated to contain twice the total volume of all the oceans on Earth. The water is liquid because of tidal heating, a process by which Jupiter's gravity, varying as Europa orbits, flexes the moon's interior and generates frictional heat. The ocean has been there, possibly continuously, for billions of years. If life arose in that ocean, and we genuinely do not know whether it did, that life is still there now, in the dark, beneath a permanent ceiling of ice. It is, by any sensible definition, alive, but the surface of Europa is dead. The surface of Europa is a frozen graveyard, with the possibility of a living basement underneath. There may be many such worlds across the cosmos, hundreds of millions, perhaps billions, of icy moons orbiting gas giants, each one potentially hosting a buried ocean. Most of those oceans, by any reasonable estimate, are sterile. A few may not be. The cosmic count of buried oceans is staggering. The cosmic count of buried ecosystems, if any exist, is unknown. Slow turn. Take a slow breath here. We are walking through a kind of double death. The visible surface of these worlds is a grave. The hidden interior may or may not be alive. The cosmos may be full of secret oceans whose biospheres we will never see, never sample, never know. Few would anticipate the third category of frozen graves, the rogue planets. Rogue planets are planets that drift between the stars without orbiting any sun. They form, in most cases, in normal planetary systems, around normal stars, and are then ejected through gravitational interactions with their siblings or with passing stars. The ejection happens early in a planetary system's history, typically within the first few 100 million years. Once ejected, the planet drifts off into interstellar space, carrying its formation heat with it for a while, slowly cooling for the rest of cosmic time. Recent surveys, particularly microlensing studies that detect rogue planets by the brief brightening they produce when they pass in front of a more distant star, have estimated that rogue planets may outnumber bound planets in the galaxy. The numbers are uncertain, but suggestive. There may be hundreds of billions of rogue planets in the Milky Way alone. Most of them are small, gas giant or super-Earth in size, but some are rocky. Most of them are dark and frozen, with surface temperatures only a few degrees above absolute zero. Yet some of them, the larger ones, may have retained enough internal heat from their formation to support liquid water beneath thick frozen crusts. The same tidal heating that warms Europa cannot operate on a starless world, but radiogenic heating from the decay of radioactive isotopes in the planet's core can. A rogue super-Earth with a thick atmosphere of hydrogen could, in principle, retain enough heat to keep liquid water beneath a frozen shell for billions of years. Some astrobiologists have speculated that the most numerous habitable worlds in the cosmos may not be planets around stars at all. They may be rogue super-Earths drifting between stars, their hidden oceans warmed by their own slow nuclear decay, their biospheres locked beneath miles of ice, completely invisible to any telescope we currently possess. No one predicts that the rogue population would turn out to be a dominant feature of the galaxy. Nobody anticipates that the most populous category of potentially habitable worlds is also the category we can barely detect. Hardly anyone anticipates the way the frozen graveyard in this picture becomes simultaneously the biggest cosmic cemetery and the biggest cosmic basement of hidden, unseen life. The point worth taking away is that frozen does not always mean dead. The frozen graveyard includes both the obvious graves, like Mars, and the ambiguous ones, like Europa, and the deeply hidden possibles, like rogue super-Earths. Most of these worlds are, in the most likely interpretation of the chemistry, sterile. A few of them are not. We do not yet know which is which. The cosmic mapping of the frozen graveyard is one of the major projects of the coming decades. Hold this image. The first graveyard, the frozen one, is by far the largest. It contains worlds that died slowly by losing their warmth. It contains worlds that may host secret biospheres beneath their surfaces. It contains worlds that drift, sunless and silent, between the stars, carrying their hidden possibilities through the dark. Tonight, we're going to spend some more time inside the Martian grave, because Mars is the one tomb in this cosmic cemetery where we have, against all early expectations, actually started taking proper inventory of what once lived there. The story of Martian astrobiology is, in itself, a slow detective novel that has been running for 60 years. In 1976, the two Viking landers touched down on the Martian surface, the first robotic visitors to actually scoop up Martian soil and look for biology. The Viking biology package included 3 different experiments designed to detect metabolic activity in the soil. The results were ambiguous in a way that has haunted astrobiology ever since. One of the experiments, the labeled release experiment designed by Gilbert Levin, produced a positive response that was consistent with biological activity. The other 2 experiments produced negative or inconclusive results. The community concluded cautiously that the positive signal was likely due to non-biological soil chemistry, possibly involving hydrogen peroxide or perchlorate compounds that had not been recognized at the time. For decades, Mars remained an open question. Then, in 1996, a team led by David McKay at NASA Johnson Space Center announced that they had found possible evidence of fossilized microbial life in a Martian meteorite, ALH 84001. The meteorite contained microscopic features that, the team argued, resembled fossilized bacteria. The announcement was made at a White House press conference. President Bill Clinton spoke about it on national television. For a moment, Mars seemed close to producing the first confirmed extraterrestrial biology. Then the case unraveled. Other research groups examining the same features in the meteorite argued that the structures could be produced by purely abiotic processes. The community gradually reached a consensus that the ALH evidence was not strong enough to support the claim of fossilized life. The case was not dismissed entirely, but it was put aside as inconclusive. Mars remained officially a planet without confirmed biology, past or present. No one expects, in the slow timeline of astrobiology, that a single meteorite announcement could so completely capture and then disappoint the public imagination. No one predicts that the Mars life question would, in the decades that followed, become a quiet, ongoing investigation rather than a single resolved answer. Absolutely no one anticipates the way the answer keeps just barely receding. With every mission adding evidence that is suggestive but not conclusive, the current generation of Mars missions, including the Mars Science Laboratory rover Curiosity and the Mars 2220 rover Perseverance, have continued to find evidence consistent with ancient habitability. Curiosity has confirmed the presence of organic molecules in Martian sediments, ancient lake beds with chemistry compatible with biological precursors, and seasonal variations in methane that could in principle have a biological source. Perseverance has cached samples of Martian rock and soil for a future sample return mission, currently planned for the 2030s, which will bring these samples back to Earth for analysis with the full suite of laboratory instruments unavailable on Mars itself. Pattern interrupt. The sample return mission is, in some ways, the most important astrobiology mission ever planned. If those samples, when analysed in terrestrial laboratories, contain unambiguous biosignatures, the question of whether Mars ever hosted life will be answered. If they do not, the absence will be informative, though not definitive, because Mars is a large planet and the samples cover only a small region. Either outcome will reshape the conversation about the frozen graveyard. Tonight, we're going to acknowledge that the frozen graveyard includes one more category that we have not yet examined in detail, and the category is more numerous than any of the others. The rogue planets that drift between the stars without orbiting any sun deserve a longer look, because their numbers are now believed to be staggering, and their potential for hidden biology, while speculative, is real. The first systematic detection of rogue planets came through microlensing surveys, particularly the OGLE project conducted at the Las Campanas Observatory in Chile and the EMOA project in New Zealand. Microlensing exploits the fact that any massive object passing in front of a more distant star will gravitationally lens that star's light, producing a brief temporary brightening. By monitoring millions of stars for these brightening events, the surveys can detect compact massive objects, including planets, that pass between Earth and the distant stars. Some of the detected events have signatures consistent with planetary mass objects with no associated stellar source, suggesting they are rogue planets drifting through interstellar space. Estimates of the rogue planet population have evolved as the surveys have grown. A landmark paper by Takahiro Sumi and collaborators in 2011 suggested that rogue Jupiter mass planets in the Milky Way might outnumber main sequence stars by a factor of 2. More recent analyses, including work from the microlensing observations in astrophysics collaboration, have suggested that the rogue planet population may be even larger when smaller mass objects are included. Some estimates now place the total rogue planet population of the Milky Way at trillions, dwarfing the stellar population by orders of magnitude. By the end of tonight, you're going to understand that this changes how we should think about the cosmic census of habitable worlds. If rogue planets are dominant by number, and if even a small fraction of them can host subsurface oceans warmed by radiogenic heating, then the largest reservoir of potentially habitable water in the cosmos is not on planets orbiting stars at all. It is on planets drifting in the dark between stars. We would not see those biospheres. We could not, with current technology, sample them. They would be entirely invisible to our sky surveys. Picture the implication. The Milky Way may contain, in its dark interstellar reaches, thousands of biospheres that have been alive for billions of years, growing in slow, steady darkness beneath miles of frozen crust, sustained by the warm decay of radioactive elements in their planetary cores. None of them would be detectable from Earth. None of them would broadcast. None of them could ever know about each other or about us. They would be, in the truest sense, hidden gardens. The cosmic graveyard in this picture might not be as dead as it appears. Some of the graves might be greenhouses. No one expects, on first hearing about rogue planets, that they could outnumber stars by orders of magnitude. No one predicts that the most populous category of potentially habitable worlds is the category we can barely detect even when they pass directly in front of more distant stars. Absolutely no one anticipates the way the cosmic census becomes more interesting and more uncertain the more we learn about it. The frozen graveyard in summary contains 4 major subcategories: the slow death rocky worlds like Mars, the icy moons with possible subsurface oceans like Europa, Ganymede, and Enceladus, the thousands of probably sterile cold rocky planets orbiting stars far from their habitable zones, and the trillions of rogue planets drifting through interstellar space, most of them dead, some of them possibly housing hidden biospheres beneath their frozen surfaces. The combined population of the frozen graveyard is staggering. It is also, in important ways, ambiguous. We do not know how much of it is dead and how much of it is sleeping. In what follows, we walk into the second graveyard, the furnace. The second graveyard begins where the first one warmed up too much. Quietly, we walk into the heat. The furnace graveyard is the one closest to home in a different way than the frozen one. It is not large by volume, not the way the icy outer dark is, but it is bright. The worlds in it are loud with infrared radiation, baked surfaces ringing with re-emitted starlight, atmospheres compressed under their own weight, oceans long since vanished into vapor, and then into nothing. If you could put a microphone on a furnace world, you would hear it hiss for the entire age of the universe. Now, let's begin with the furnace graveyard. The first member of the furnace graveyard, the one nearest to your home star, is Venus. You have looked at Venus more often than you may realize. On many evenings, it is the brightest object in the western sky after sunset, brighter than every star. On many mornings, it is the last point of light to fade before dawn. Ancient astronomers, working with their unaided eyes, knew Venus as the morning star and the evening star. They built temples around its appearances. They timed festivals to its motion. Venus has been a companion to human civilization for as long as we have looked up. And Venus is dead. Walk with me as we trace what Venus was and what Venus became, because the story of Venus is the closest thing the solar system has to a warning. Venus is, by every reasonable measure, Earth's twin. Its mass is about 81% of Earth's. Its diameter is about 95% of Earth's. Its bulk composition, as far as we can determine, is roughly the same. It formed at roughly the same time from roughly the same material in roughly the same neighborhood of the early solar system. By every chemistry textbook standard, Venus and Earth should have evolved into broadly similar worlds. They did not. Earth is blue, with oceans, with continents, with a biosphere that has been continuously evolving for nearly 4 billion years. Venus is grey-yellow, with a surface temperature of about 860 degrees Fahrenheit, with an atmospheric pressure 90 times greater than Earth's, with no liquid water anywhere, with clouds of sulfuric acid hanging permanently in its upper atmosphere. Venus is the hottest planetary surface in the solar system. It is hotter than the dayside surface of Mercury, even though Mercury is closer to the Sun. Venus is hotter than the sun-facing side of most of the rocky moons we know. The heat is generated and held by an atmosphere of nearly pure carbon dioxide, more than 96% by composition, that has run away into a thermal cascade from which no slow climate process can rescue it. A small pause. The story of how Venus became Venus is, in cosmic terms, the story of one of the most common ways a habitable world can die. The story begins with a young Venus that may have been habitable, possibly even more habitable than Earth at the start. Modern climate simulations, including work by Michael Way and his collaborators at NASA Goddard, suggest that for the first several hundred million years, perhaps even the first 1 or 2 billion years, Venus may have had shallow oceans, a moderate climate, and surface conditions broadly compatible with the early stages of life. Cloud feedback in those models kept the surface cool enough for water to be stable. Then something changed. The Sun, slowly brightening over its main sequence lifetime, pushed Venus past a climate threshold. The shallow oceans began to evaporate. Water vapor, a powerful greenhouse gas, accumulated in the atmosphere. The accumulation warmed the surface further. Warming evaporated more water warmed more. The process, which climate scientists call a runaway greenhouse, fed on itself until the entire ocean was in the atmosphere as steam. The surface was many hundreds of degrees, and the hydrogen molecules in the water vapor were being slowly stripped off into space by the solar wind. Over a few 100 million years, Venus lost its water entirely. What was left was an atmosphere of carbon dioxide and the slow, weathering products of a sterilized surface. Walk slowly through the implications. The runaway greenhouse is not unique to Venus. It is a generic mode of climate failure for any rocky planet with sufficient carbon dioxide stocks and water that orbits too close to its star. Modern habitable zone calculations include an inner edge, beyond which a rocky world will, with high probability, run away into a Venus-like state. For our Sun, the inner edge of the habitable zone today sits at roughly 95% of Earth's orbital distance. Venus, at 72% of Earth's distance, is well inside that boundary. Earth, by a slim margin, is on the safe side. Stay with this thought. The slim margin is the part of the story that haunts modern climate scientists. A planet that formed 20% closer to its sun than Earth would have followed the Venusian path. A planet that formed only 5 or 10% closer might have done the same. The window for a habitable rocky world is narrower than the lay impression of the habitable zone tends to suggest. The inner edge is sharp. The cliff is real. Now consider the cosmos. The exoplanet surveys have found, with increasing confidence, that hot rocky planets orbiting close to their stars are extraordinarily common. The Kepler mission established that, around Sun-like stars, planets between roughly Earth and Neptune in size are extremely abundant, and many of them orbit at distances well inside the inner edge of the habitable zone. The K2 mission, the TESS mission, and ground-based radial velocity surveys have continued to fill in the picture. A substantial fraction, perhaps tens of billions in our own Milky Way alone, of the rocky planets in the galaxy are baking. Some of them are Venus-like. Others are even more extreme, the so-called lava worlds, where the surface is partially molten. Move with me as we visit one of the most striking examples. K2-141b is a hot super-Earth orbiting an orange dwarf star about 200 light-years from Earth. Its orbital period is just under 7 hours. It is so close to its star that its dayside temperature, by direct thermal measurement, is over 2,500 degrees Fahrenheit. At that temperature, rock vapor, iron melts, silicates flow. The dayside of K2-141b is a literal lava ocean. The terminator, where day meets night, is a region where rock rain falls from a vaporized rock atmosphere onto a molten rock surface. K2-141b is, in any honest sense, a world that died before it could begin. The conditions never permitted biology. The chemistry that might have led somewhere was vaporized. Hold the picture as we acknowledge how common such worlds are. Lava worlds, ultra-hot Jupiters, and Venus-like rocky planets together constitute a substantial fraction of all known exoplanets. The number of such worlds in the observable universe is plausibly on the order of 10 to the 19th or 20th power. The furnace graveyard is enormous. It is also, for our purposes tonight, dramatically more uniform than the frozen graveyard. The frozen graveyard contains the possibility of hidden life beneath the ice. The furnace graveyard contains no such possibility. Heat sterilizes thoroughly. A lava ocean is not a place where biology hides. It is a place where biology has been chemically erased. Slow down here. The furnace graveyard contains another subtle category that deserves a moment: the hot Jupiters. Hot Jupiters are gas giants, planets roughly the mass of Jupiter or larger, that orbit very close to their stars, often with periods of just a few days. The first exoplanet discovered around a Sun-like star, 51 Pegasi b, was a hot Jupiter. Hundreds more have been found since. They are in many ways the most studied class of exoplanets because their large size and close orbits make them easy to detect. Hot Jupiters did not form where they currently orbit. The temperatures that close to a star are too high for gas giants to assemble. They formed further out in the colder regions of their planetary systems and then migrated inward over time, dragged by interactions with their natal disks or with their planetary siblings. As they migrated, they passed through the regions where rocky habitable worlds might have formed. The migration would have either destroyed those worlds outright, by direct collision or scattering, or pushed them onto unstable orbits that ejected them from the system. A hot Jupiter is, in a sense, the ghost of all the smaller habitable planets it consumed or expelled on its way to its current position. The implication is dark, in a way the basic furnace story is not. The hot Jupiter graveyard is not a graveyard of planets that died after life began. It is a graveyard of planets that never got the chance to form, because a larger sibling came through first and rearranged the neighborhood. The number of habitable worlds that were eliminated this way is, by extrapolation from the hot Jupiter frequency in the trillions. The cosmos is, in this picture, filled with the absences of worlds that should have existed and do not, because their formation environments were swept clean by migrating giants. The textbook does not anticipate the way migration sterilizes whole systems. Few of us anticipate that the most common detected planets, the hot Jupiters, are simultaneously some of the strongest indicators of how brutal planet formation can be. The intuition does not anticipate the way a single massive sibling can erase the possibility of life for an entire stellar system. Mark this moment. The furnace graveyard is the second category, and it is dramatically different from the first. Frozen worlds preserve their chemistry. Furnace worlds erase it. Frozen worlds may hide biospheres beneath ice. Furnace worlds destroy any chemistry that might have led to biospheres. Frozen worlds are graves where the body is preserved. Furnace worlds are graves where the body has been cremated. Together, the frozen and furnace graveyards account for the overwhelming majority of rocky worlds in the cosmos. By some estimates, more than 90% of all rocky planets orbiting all stars in cosmic history fall into one of these two categories at some point in their evolution. The vast majority of the cosmic rocky world census is dead before any star has finished its life. The question is not whether the cosmos is full of dead worlds. The question is whether there is any meaningful number of worlds that are anything else. Before we walk into the third graveyard, the irradiated worlds, take a long pause with me. Before we continue. Why this channel exists. If you have made it this far into a story about cosmic death, you are not the casual viewer the algorithms expect. You are the person for whom this channel exists. Long-form cosmology, at the pace of sleep, is not what the platform rewards. It is what we make anyway, because we believe that the universe, taken slowly, is more interesting than the universe taken fast. We believe that a question about the cosmic graveyard is better asked over hours than over minutes. We believe that you, the person still listening, deserve a place where the cosmos can be experienced at a human pace, not a viral pace. If that resonates with you, the simplest gift you can give us is to subscribe. Subscribing tells the platform that long, calm cosmic work is worth surfacing for the next person who is looking for it. It also tells us, the people who make these videos, that the work is reaching the audience it was meant for. If you've already subscribed, thank you. Truly. If this is your first long-form cosmic night with the channel, welcome. There are many more like it in the queue. A second small ask. If, on Spotify, this episode finds you on quiet nights when you cannot sleep, consider following the show there as well. The audio versions are tuned for the same purpose, the same pace, the same length. We want you to have a slow companion across both surfaces. Subscribe on YouTube, follow on Spotify and the next graveyard, and the one after that will quietly find you whenever you're ready to walk through them. Tonight, we're going to spend a longer stretch with Venus, because Venus is the world we have most carefully diagnosed as a graveyard, and the diagnosis has implications for thinking about all the other graveyards we will visit. The serious modern exploration of Venus began in 1962, when the Mariner 2 spacecraft made the first successful planetary flyby in history, passing within 22,000 miles of the Venusian surface. The thermal infrared instruments on Mariner 2 measured the planet's bulk temperature for the first time, confirming that Venus was extraordinarily hot. The older debates about whether Venus might host swamp-like surface conditions dating back to the early 20th century were settled in a single afternoon. Venus was a furnace. The Soviet Venera program, between 1961 and 1984, became the only sustained effort to actually land probes on the Venusian surface. The Venera landers had to be engineered to survive surface conditions hostile beyond any other planetary environment we have visited. The atmospheric pressure at the surface is 92 times Earth's atmospheric pressure, equivalent to the pressure at about 3,000 feet below the surface of Earth's oceans. The atmospheric temperature is over 860 degrees Fahrenheit. The atmosphere is composed almost entirely of carbon dioxide, with clouds of sulfuric acid suspended at altitudes of about 30 miles. Venera 7 became the first probe to transmit data from the Venusian surface in 1970. The probe survived for 23 minutes before its systems failed. Venera 13 and 14, in 1982, transmitted the first colour images of the Venusian surface, showing a rocky orange-red landscape under a hazy yellow sky. The lander survived for approximately 2 hours before succumbing to the heat and pressure. No probe has touched the Venusian surface since 1985, when Vega 2 transmitted its final atmospheric data. No one expects, on hearing about a planetary surface environment, that engineering robust enough to survive deep ocean pressures and oven temperatures simultaneously would still only buy you a few hours of operating time. No one predicts that the most successful Venus landers, after nearly 2 hours of operation, would be considered triumphs of engineering rather than failures. Absolutely no one anticipates the way the surface of Venus is, in its own quiet way, more hostile than the surface of any other known world in the solar system. Pattern interrupt. The brutality of the Venus surface environment is, in itself, scientifically informative. Venus shows us what a runaway greenhouse looks like once it has completed its work. The carbon dioxide that was once locked into surface rocks and oceans has been driven out by the heat and now sits in the atmosphere as a thick blanket of greenhouse gas. The water that was once present has been broken into hydrogen and oxygen by ultraviolet radiation, with the hydrogen escaping to space and the oxygen reacting with surface minerals. The chemistry has gone in a one-way direction. The process cannot be reversed by ordinary climate cycles. Venus is not in a stable state that could, in principle, return to habitability. Venus is in the final equilibrium of a climate that has burned through everything that could buffer it. Tonight, we're going to walk a step further, because the most chilling aspect of Venus is not what it is now, but how recently it became this way. The traditional view, supported by older climate models, held that Venus has been hot for essentially the entire age of the solar system. Recent work, particularly the climate modelling done by Michael Way at NASA Goddard and his collaborators since 2016, has suggested that Venus may have remained habitable for a much longer fraction of its history than previously assumed. In one set of plausible model scenarios, Venus had surface oceans and a temperate climate for as long as 2 billion years, with the runaway greenhouse only beginning a few 100 million years ago. If those scenarios are correct, then Venus was alive, or at least viable for life, more recently than was once thought. The transition from habitable to graveyard may have occurred at a time when Earth was already hosting complex multicellular organisms. The death of Venus, in this picture, was not a primordial event. It was a relatively recent catastrophe, happening on a planet that had been pleasant for longer than the time between the rise of complex animals on Earth and the present day. The implication is sobering. If Venus could maintain habitability for 2 billion years and then lose it within geologically recent times, then the boundary between habitable and uninhabitable for any rocky planet is not a static threshold. It is a slowly moving line. Planets that are habitable now may not remain so. Earth itself, as the sun continues to brighten over the next billion years, will eventually face the same climate threshold that Venus crossed. The standard models suggest Earth will become uninhabitable in roughly 1 billion years as the sun's increasing luminosity drives the inner edge of the habitable zone past our orbit. By that time, our oceans will boil, our atmosphere will fill with steam, and we will follow Venus into the same runaway greenhouse end state. No one predicts, on first thinking about cosmic timescales, that Earth's habitability is genuinely finite. No one expects that the same fate that made Venus a graveyard will eventually claim our own world. Absolutely no one anticipates that the cosmic graveyard of furnace worlds will, on a long enough time scale, include Earth. By the end of tonight, you're going to understand that the furnace graveyard is not just a category of worlds that died long ago. It is a category that continues to be filled, as habitable planets across the cosmos eventually cross their climate thresholds and convert from blue to grey. Some are converted early by formation chemistry that left them inside the runaway boundary from the start. Some are converted late, like Venus may have been, by slowly brightening stars that gradually push the boundary outward. Eventually, every rocky planet in a stable orbit around any main sequence star will be claimed by the inner edge of its star's habitable zone as the star brightens with age. The furnace graveyard is being filled, slowly and continuously, by every habitable world that has ever existed or ever will exist. Tonight, we should also visit one of the most extreme examples of the furnace graveyard ever discovered, the planet known as 55 Cancri E, orbiting a sun-like star about 40 light-years from Earth. 55 Cancri E is about 8 times the mass of Earth and about 2 times its radius. Its orbital period is just over 17 hours. It is so close to its star that its dayside surface temperature is estimated at over 4,000 degrees Fahrenheit, hot enough that the rocky surface is partially molten. The atmosphere of 55 Cancri E, if it exists at all, is exotic. Spectroscopic observations suggest the dayside may have an atmosphere of vaporized rock, including silicate dust and metallic vapors. JWST observations published in 2024 detected the signatures of carbon dioxide and carbon monoxide in the planet's dayside spectrum, suggesting that some form of secondary atmosphere is present despite the extreme conditions. The night side, by contrast, is much cooler, possibly cool enough for the vaporized rock to condense into clouds of mineral dust that fall as a kind of rocky rain. No one expects, when first envisioning planetary surfaces, that any world could have weather systems involving the precipitation of rock. No one predicts that the chemistry of an ultra-hot rocky planet would produce vapors and condensates that mimic the rain cycles of cooler worlds, but with silicate instead of water. Absolutely no one anticipates the way the cosmic graveyard contains worlds whose deaths are not just hot, but exotic in their chemistry to the point of strangeness. 55. Cancri E is, in its way, a poster child for the furnace graveyard. It illustrates what happens to a rocky world when the orbital geometry leaves no margin for habitability. The planet probably never had liquid water. It probably never could have. The chemistry was sterilizing from the start. The world is, in a sense, a stillborn member of the cosmic family of rocky planets. Its biology never had a chance to begin. Now let us return to the cosmos. The third graveyard is waiting. Now let's begin with the third graveyard. The third graveyard is, by number, perhaps the largest of all. It is the graveyard of worlds that orbit red dwarf stars. Take a moment to sit with the demographics first, because the demographics are the whole reason this graveyard matters so much. Of all the stars in the Milky Way, roughly 75% are red dwarfs, M-class dwarfs, in the standard astronomical naming. Small, cool, dim stars with masses ranging from about 8% to about 60% of the Sun's mass, and surface temperatures from about 3,000 to about 4,000 degrees Fahrenheit. They are common because small stars are common. The initial mass function of star formation strongly favours small stars over large ones. For every Sun-like star in the galaxy, there are about 3 or 4 red dwarfs. The same demographics apply to the rest of the cosmos. 3/4 of all stars in every galaxy we have studied appear to be red dwarfs. The cosmic census, therefore, is dominated by these small, cool stars. Any honest accounting of habitable worlds in the cosmos has to start with the question of whether red dwarf planets are habitable. The answer, as best we can tell from the past decade of work, is complicated and not very encouraging. Together, we walk through the basic problem. Red dwarfs are dim. To receive enough energy to maintain liquid water on a planet's surface, that planet has to orbit very close to the star. The habitable zone around a typical red dwarf sits at distances comparable to Mercury's orbit around the Sun, or even closer. For the very smallest red dwarfs, the habitable zone is so close that planets in it complete an orbit in just a few days. Close orbits create 3 problems for habitability. The first is tidal locking. The second is stellar flaring. The third is atmospheric stripping. Each of them, on its own, is a serious obstacle. Together, they make habitability around red dwarfs a precarious proposition. Tidal locking is the simplest. When a planet orbits very close to its star, the star's gravitational gradient across the planet is strong enough to dissipate the planet's rotational energy over geological time. The planet ends up with one face permanently turned toward the star and the other face permanently turned away. This is what the Moon does relative to Earth, and what Mercury does to some extent relative to the Sun. For red dwarf planets in the habitable zone, tidal locking is essentially universal. Within a few 100 million years of formation, the planet is locked. Notice the shift. A tidally locked planet has a permanent day side, where the star is always in the sky, and a permanent night side, where the star never rises. The day side is hot, possibly very hot. The night side is cold, possibly very cold. Without an atmosphere to redistribute heat, the day side becomes a baked desert, and the night side becomes a frozen waste. With a thick enough atmosphere, however, heat can be redistributed efficiently enough to maintain habitable conditions across both hemispheres. Climate models have shown that a moderately thick atmosphere with appropriate composition can produce a tidally locked planet with a habitable terminator zone, where the day-night boundary forms a permanent band of moderate temperature stretching from pole to pole. The terminator zone, if it exists, is one of the most evocative habitable environments in the cosmos. Imagine a permanent sunset, a band of red light circling the planet, with a frozen wasteland on one side and a baked desert on the other. Civilizations on such a world, if they ever arose, would live entirely within the terminator. They would build cities along the line where day meets night. Their sky would never change. Their seasons, if they had any, would be slow climate cycles rather than daily rhythms. Their experience of time would be unlike anything humans have ever known. But tidal locking is not the worst of the three problems. The worst is the flaring. Hold this image. Red dwarfs are not steady stars. They are violently active. Their magnetic fields are tangled and strong relative to their size, and they release that energy in frequent, sudden, intense flares. A typical red dwarf may produce a flare equivalent to the strongest flares ever recorded on the Sun every few days, on average. Some red dwarfs produce flares of much greater magnitude, the so-called superflares, which can release energy equivalent to 1,000 times the larger solar flares. Superflares occur on timescales of months to years on many young red dwarfs, and on timescales of decades to centuries on older ones. For a planet orbiting in the close inhabitable zone of a red dwarf, these flares are catastrophic. They deliver ultraviolet and X-ray radiation directly to the planet's upper atmosphere. They strip ions from the atmosphere, exactly like the solar wind on early Mars, but with much greater intensity. They generate energetic particle fluxes that penetrate down to the surface in some cases. Over the lifetime of a typical red dwarf, which can extend for trillions of years, the cumulative flaring delivers more ionizing radiation to a habitable zone planet than the Sun delivers to Earth by orders of magnitude. The textbook does not anticipate the way a small, dim star can sterilize its closest world so thoroughly. Few of us anticipate that the most common type of star in the cosmos is also one of the most hostile to its own planets. Almost nobody anticipates that habitability around red dwarfs requires not just the right distance, but a planet capable of regenerating its atmosphere faster than the flares can strip it away. Watch how the flaring problem plays out in real systems. The Proxima Centauri system, our nearest stellar neighbour, hosts at least 3 confirmed planets. Proxima b, the most famous of them, orbits in what would conventionally be called the habitable zone of the star. It receives about 65% as much stellar radiation as Earth receives from the Sun. By the simple temperature calculation, Proxima b could host liquid water. The problem is that Proxima Centauri is a particularly active red dwarf. In 2016, the Pale Red Dot collaboration discovered Proxima b. In the years since, multiple observation campaigns have detected powerful flares from the star. A 2019 event recorded by the Atacama Large Millimeter Array delivered a burst of radiation to Proxima b roughly 4,000 times stronger than the largest solar flare Earth has experienced in modern times. Several similar events have been recorded since. The cumulative dose, integrated over even a few 100 million years, would strip a moderate atmosphere entirely and sterilize any surface biology that lacked deep protection. Proxima b is, in the most likely current interpretation, a graveyard. It may have had an atmosphere once. It may have had surface water once. Whether it ever hosted biology is unknown. What is clearer is that, by now, the surface is almost certainly inhospitable. The radiation has done its work for billions of years. Whatever was there is gone. For the next stretch, we visit the most studied case of all, the TRAPPIST-1 system. Discovered in 2016 and characterized in detail over the following years, TRAPPIST-1 hosts 7 Earth-sized planets in tight orbits around an ultra-cool red dwarf about 40 light-years from Earth. 3 of those planets, TRAPPIST-1 F and G, sit within the conservative habitable zone of the star. The system has been one of the most exciting exoplanet discoveries of the past decade. It has also been one of the most sobering. The TRAPPIST-1 star is highly active. James Webb Space Telescope observations of the inner planets have shown that they likely possess little to no atmosphere. The flaring history of the star, combined with the close orbits of its planets, has stripped them of whatever atmospheres they may have formed with. The outer planets, including the 3 in the conventional habitable zone, may have retained more of their atmospheres, but the early system bombardment was severe. JWST observations of TRAPPIST-1c in particular have shown a surface temperature consistent with a bare rocky world, with no significant atmosphere to redistribute heat. The point worth taking away is that TRAPPIST-1, the most famous and most studied multi-planet habitable zone system we have ever found, may be a complete graveyard. 7 worlds, 4 of them in or near the habitable zone, may all have been sterilized by their own star's activity within the first few 100 million years of the system's history. The cosmic statistics implied are stark. If TRAPPIST-1 is typical of red dwarf systems, then a substantial fraction of all the planets in the most common stellar environment in the cosmos are dead. Pause and notice. 3/4 of all stars are red dwarfs. The habitable zones around red dwarfs are too close for safety. The planets in those zones are tidally locked, flared into sterilization, or stripped of their atmospheres. The cosmic statistics, if these patterns hold, suggest that the vast majority of potentially habitable rocky worlds in the universe are also dead, simply because of the kind of star they orbit. There is some hope in the picture, but it is a quiet hope. Older red dwarfs are calmer than younger ones. After a few billion years, the flaring decreases substantially. A planet that survives the early flaring epoch with some atmosphere intact may then enjoy a long, calmer period of relative stability. Some climate models, including work by Robin Wordsworth and others, have suggested that planets with thick carbon dioxide atmospheres or with significant water inventories may be able to retain habitable conditions for billions of years around quieter, older red dwarfs. But the early window is brutal. Most red dwarf planets that lose their atmospheres early do not get them back. The few that survive intact are the survivors of a selection process that, by every available estimate, eliminates the majority of candidates. The cosmic count of planets that successfully run the red dwarf gauntlet is much smaller than the count of planets that start it. Slow turn, let the picture settle. The 3rd graveyard is the most numerous because the host stars are the most numerous. The 3rd graveyard is also the most poignant because the deaths happened so early. The planets here did not die after billions of years of biological evolution, like Mars. They did not slow bake over an even longer climate cascade like Venus. They were stripped, often in their first cosmic infancy, by the relentless ultraviolet rage of stars that are too small to be steady and too active to be safe. The biology never had time to begin in most cases. The chemistry was raked off the surface before it could find its first stable configuration. There is one more aspect of the irradiated graveyard that we should mark before walking on. The atmosphere stripping that kills red dwarf planets is not unique to red dwarfs. It happens, in milder form, to planets orbiting more sun-like stars during the violent early phases of their own stars. The young sun was much more active than the present sun. In the first few 100 million years of its main sequence life, our own star produced flares and ultraviolet output many times its current level. Earth survived, helped by its strong magnetic field and its rapid recovery of an atmosphere from its volcanic interior. Mars, smaller and less protected, did not. Venus, closer to the heat, ran away in the other direction. The early stellar activity phase is, in effect, a universal filter that every potentially habitable planet has to survive. Around red dwarfs, the filter is harsh enough to eliminate most candidates. Around sun-like stars, the filter is harsh enough to eliminate many. Around bigger stars, the filter is harsh, and the star also burns out too quickly to allow biological evolution to begin. The window for habitability, integrated over the cosmic star census, is narrower than it first appears. The takeaway is that the third graveyard, the irradiated one, may be the single largest by raw count of dead worlds. It dwarfs the others in absolute numbers because of the demographics of star formation. It is also the most subtly dispiriting, because it implies that the most common stellar environment in the cosmos is not friendly to the kinds of long-lived stable atmospheres that biology needs. Tonight, we're going to step into the technical heart of red dwarf habitability, because the language of habitable zones, biosignatures and stellar activity has become precise enough over the past decade that the picture can be drawn with more confidence than it could even 5 years ago. The classical habitable zone is defined as the range of orbital distances around a star where a rocky planet with an Earth-like atmosphere could maintain liquid water on its surface. The original framework, developed by James Casting at Penn State in the early 1990s, calculated the inner and outer edges of the zone based on assumptions about atmospheric composition, planetary albedo, and the greenhouse effect of various gas inventories. For a sun-like star, the conservative habitable zone in the casting model extends from roughly the orbit of Venus to roughly the orbit of Mars. For red dwarfs, the habitable zone is much closer to the star, often closer than the orbit of Mercury around the Sun. The inner edge of the red dwarf habitable zone is also more complicated because the stronger ultraviolet output of young red dwarfs can drive water loss from the planet's atmosphere through photodissociation. A planet at the inner edge of a red dwarf habitable zone may be habitable in terms of temperature, but uninhabitable because its water is being continuously broken into hydrogen and oxygen by ultraviolet light, with the hydrogen escaping to space. The community has therefore moved toward a more refined concept, sometimes called the abaikogenesis zone, or the radiation-resistant habitable zone. These newer frameworks attempt to identify the orbital region around a red dwarf, where a planet could not only maintain liquid water, but also retain its atmosphere and avoid being sterilized by ultraviolet radiation. The radiation-resistant zone is, in general, much narrower than the conventional habitable zone, and for the most active red dwarfs it may not exist at all. Some red dwarfs, particularly the youngest and most active, may have no orbital region where a rocky planet could maintain both liquid water and a stable atmosphere. No one expects, on first hearing about habitable zones, that the simple temperature-based definition would prove inadequate when applied to the most common stars in the cosmos. No one predicts that habitability requires the conjunction of multiple separate conditions, each one of which can be independently violated. Absolutely no one anticipates the way the cosmic count of truly habitable planets shrinks as the framework is refined. By the end of tonight, you're going to understand that this refinement is one of the most important quiet developments in astrobiology over the past decade. The earlier optimism about the abundance of habitable planets was based on the simpler temperature-based definition. As the definitions have been refined, the count has gone down. Not by orders of magnitude, but by enough to matter. The cosmic graveyard in the updated picture is denser than the simpler model implied. Tonight, we're going to walk through one specific system that has become a test case for the new framework. The planet LHS 1140b orbits a red dwarf about 48 light-years from Earth in the constellation Cetus. It was discovered through the MERTH project, a ground-based survey looking for transits of nearby red dwarfs. LHS 1140b is a super-Earth, about 6 times the mass of Earth and 1.7 times its radius. Its orbital period is about 25 days, placing it in the conventional habitable zone of its star. What makes LHS 1140b interesting is that its host star is unusually quiet for a red dwarf. The star is old, perhaps 5 billion years old, and its rotation rate is slow. The stellar activity that would be expected from a younger red dwarf is largely absent. The flaring rate is low. The X-ray and ultraviolet output is moderate. The radiation-resistant habitable zone calculation suggests that LHS 1140b sits comfortably within a region where a rocky planet could plausibly retain both an atmosphere and liquid water. The JWST observations of LHS 1140b conducted in 2024 have produced suggestive but not yet definitive results. The transmission spectrum of the planet's atmosphere measured during a transit shows possible features consistent with a nitrogen-dominated atmosphere with some water vapour. The results are at the edge of detection, and further observations are needed to confirm the interpretation. But the early signs are encouraging. LHS 1140b may be one of the small minority of red dwarf planets that has actually survived its host star's early activity and retained a habitable atmosphere. Pattern interrupt. The case of LHS 1140b is instructive because it suggests that not all red dwarf planets are equal. The ones orbiting old, quiet red dwarfs are in a much better position than the ones orbiting young, active red dwarfs. The TRAPPIST-1 system, by contrast, orbits a young and active red dwarf, and its planets show signs of having lost their atmospheres. The Proxima Centauri b system orbits a moderately active red dwarf, and the prospects for atmospheric retention are uncertain. The Wolf 1069 system, discovered in 2023, orbits a quieter star and may be more analogous to the LHS 1140 case. The cosmic implications are mixed. The vast majority of red dwarf systems, including most of the ones currently within human survey reach, orbit younger or moderately active stars where atmospheric retention is unlikely. A small fraction, perhaps 5 to 10% based on current estimates, orbit older, quieter stars where habitability remains plausible. If this fraction holds across the cosmos, then the count of truly habitable planets around red dwarfs is much smaller than the simple stellar census would suggest, but it is not zero. The cosmic population of red dwarf habitable planets is probably in the millions to low billions in our galaxy alone, not the tens of billions that the optimistic count would imply. No one predicts, in any straightforward way, what the actual fraction of habitable red dwarf planets will turn out to be. No one expects that the answer will be either zero or unity. Absolutely no one anticipates that the next generation of atmospheric characterization, expected from JWST follow-up programs and from the Habitable Worlds Observatory planned for the 2030s, will produce a definitive number. But the work is being done. The answer is coming. Tonight, we should also acknowledge one final consideration about the irradiated graveyard. The atmospheric loss processes that kill red dwarf planets do not act with equal severity on all atmospheric compositions. A thin atmosphere is easier to strip than a thick one. A water-rich atmosphere is more vulnerable to photodissociation than a carbon dioxide atmosphere. A planet with strong volcanic outgassing can replenish its atmosphere faster than one without active geology. Some red dwarf planets, the the ones with the right combinations of atmospheric mass, composition, and volcanic activity, may be able to survive even active host stars by continuously rebuilding what is lost. The cosmic count of such survivors is hard to estimate. The relevant geological processes depend sensitively on planet mass, composition, and history. A super-Earth with a thick carbon dioxide atmosphere and active volcanism may be quite robust against atmospheric stripping. A smaller Mars mass world, even if it formed with a substantial atmosphere, will lose it quickly without a strong magnetic field. The variability among individual systems is large, and the statistical distribution of outcomes is only beginning to be understood. The takeaway from this section, in summary, is that the irradiated graveyard is large but not as monolithic as it first appears. Most red dwarf planets are graveyards. Some are not. The ones that are not tend to orbit quiet stars and possess robust atmospheres with active geological recycling. The cosmic count is in the millions to low billions across the Milky Way, with the total across the observable universe in the hundreds of trillions. The graveyard is enormous, but the surviving population, if our current understanding is roughly correct, is not entirely negligible. In the next graveyard, we walk into the most violent of all, the blast zones. The fourth graveyard is the most violent. The deaths here are not slow, they are not climatic, they are not chemical strippings over hundreds of millions of years. They are sudden, complete, and often surprisingly large in their reach. The fourth graveyard is the graveyard of blast zones. Step by step, we walk through three kinds of cosmic catastrophe that can sterilize a planet across light years of distance in a matter of seconds to days, regardless of how robust the planet's atmosphere or magnetic field had been before the event. The first is the nearby supernova, when a massive star, more than about 8 times the mass of the Sun, exhausts its nuclear fuel and collapses. The resulting explosion releases an extraordinary amount of energy in a short time. The peak luminosity of a typical core collapse supernova rivals the combined output of an entire galaxy for several weeks. The shock front of ejected material travels outward at thousands of miles per second. The high-energy radiation, particularly the gamma rays and X-rays produced in the early phase of the explosion, propagates outward at the speed of light. For a planet at a moderate distance from the explosion, say a few tens of light years, the consequences are catastrophic. The initial flash of ultraviolet, X-ray and gamma radiation, lasting for hours to days, is intense enough to destroy the planet's ozone layer in seconds. With the ozone gone, the surface is exposed to the full ultraviolet output of the planet's own star, plus the lingering high-energy radiation from the supernova itself. Surface life that depends on the ozone layer for protection is killed, either immediately or over the following weeks. The second wave, the supernova ejector itself, arrives later, weeks to centuries later, depending on distance, travelling at a few percent the speed of light. The ejector carries radioactive isotopes, particularly iron-60 and aluminum-26, which can fall onto the planet's surface and seed long-term radiation damage. Even more importantly, the ejector can compress the planet's local interstellar environment, altering the cosmic ray flux for thousands of years. Cosmic ray exposure during this period can produce mutagenic effects in surviving biology and disrupt atmospheric chemistry on a global scale. Settle in here. The combined effect of a nearby supernova is, for a habitable planet within the danger radius, a catastrophe from which biology either does not recover or recovers only after a major extinction. The estimated lethal radius depends on the type of supernova, the planet's atmospheric structure, and the planet's magnetic field. But for a typical core collapse event, planets within about 30 light-years are at substantial risk of mass extinction. Planets within 10 light-years are at risk of complete sterilization. The Earth itself has, in all probability, passed close enough to several supernova events over its history to receive measurable doses. Sediment cores from the deep ocean have revealed elevated levels of iron-60 in layers dated to about 2 to 3 million years ago, and again in older layers dated to about 7 million years ago. The most likely explanation is that 2 supernova events occurred within about 300 light-years of Earth in the relatively recent geological past, and Earth passed through the ejected material as the shock front swept by. Some researchers have suggested that these events may have contributed to extinction patterns in the marine fossil record of those eras, though the connection is not yet firmly established. Notice the turn. The Earth survived. Most species survived. But the events left a chemical fingerprint in radioactive iron that we can still measure today. We are in a real sense a planet that has been brushed by supernova ejecta multiple times. We have been lucky. Many planets across the cosmos have not. The galaxy contains many regions where the supernova rate is high enough that habitable planets within them face significant risk over their lifetimes. The bulge of the Milky Way, the central region within about 10,000 light-years of the galactic center, has a higher density of stars and a higher rate of supernova. The spiral arms, where star formation is concentrated, also have elevated rates. By contrast, the outer disk and the regions between spiral arms have lower rates and are, in this respect, somewhat safer for long-term biological evolution. This consideration leads to the concept of a galactic habitable zone. The galactic habitable zone is the region of the galaxy that is sufficiently rich in heavy elements to allow rocky planets to form, but sufficiently distant from the dense, supernova-prone regions to avoid frequent sterilization. Our Sun sits in roughly the middle of this zone, about 26,000 light-years from the galactic center, in a relatively quiet region between major spiral arms. The placement is, in part, what allowed Earth to enjoy 4 billion years of biological continuity without major sterilization events. The textbook does not anticipate the way galactic geography matters for biological survival. Few of us anticipate that the position of a solar system within its galaxy could be a major filter on whether life survives long enough to become complex. Almost nobody anticipates the way the cosmic supernova rate has been, for most habitable planets, a slow-ticking clock. The second kind of blast zone catastrophe is the gamma-ray burst. Gamma-ray bursts are the most luminous explosions in the universe. They release more energy in a few seconds than the Sun will release in its entire 10 billion year lifetime. The most powerful of them, the so-called long gamma-ray bursts associated with the collapse of certain massive stars, can deliver lethal doses of gamma radiation to planets thousands of light-years away. The mechanism is similar in principle to the supernova mechanism, but the energies are much higher and the focus is much narrower. Gamma-ray bursts are believed to be beamed, with their radiation concentrated into 2 narrow jets pointing in opposite directions from the collapsing star. A planet caught directly in one of those jets, even at distances of thousands of light-years, can experience a lethal radiation dose in seconds. Planets not in the jet path receive no significant radiation from the same event. The geometry of gamma-ray burst sterilization is therefore selective. Some planets are killed at extraordinary distances. Most planets are spared. Slowly, we trace the cosmic implications. Gamma-ray bursts occur across the universe at a rate of roughly 1 per day. Most of them are in distant galaxies and pose no threat to any specific planet of interest. But within our own galaxy, gamma-ray bursts may occur, on average, once every few 100,000 to a few million years. If one such event occurs with its jet pointed at Earth from anywhere within, say, 6,000 light-years, the consequences could be severe. The Ordovician-Silurian mass extinction, which occurred about 440 million years ago and eliminated roughly 60% of marine species, has been hypothesized by some researchers, notably Adrian Mellott and his collaborators, to have been triggered by a gamma-ray burst within the Milky Way. The case is not conclusive, but the timing and the pattern of extinction, particularly the targeting of organisms that lived in shallow water and were exposed to ultraviolet, is at least consistent with such an event. The evidence is suggestive rather than definitive, but it is suggestive enough to be taken seriously. Hold the thought. Even if the Ordovician event was not caused by a gamma-ray burst, the cosmic rate of such events implies that Earth, over its 4 billion-year history, has likely been hit by one or more bursts at least at the edge of the lethal range. We may have lost half our biodiversity in such an event without noticing it as anything other than a mysterious extinction in the fossil record. For planets in denser galactic environments, gamma-ray bursts are more frequent threats. Some recent work by James Annis, Brian Lackey and others has explored the idea of a temporal gamma-ray burst-driven Fermi paradox solution. In the early universe, when galaxies were more compact and star formation rates were higher, gamma-ray bursts occurred much more often. Habitable planets in those eras may have been sterilized at frequencies that prevented complex life from establishing itself. Only in the past few billion years, as the cosmic gamma-ray burst rate declined, has the universe become quiet enough for sustained biological evolution. The implication is that the cosmos may have been, until recently, too violent for life to develop the long uninterrupted runs of stability that complex biology requires. The current era, the past few billion years, may be the first time in cosmic history when sufficient quiet has been available across enough galactic real estate for civilizations like ours to begin to emerge. We may be, in a meaningful sense, near the start of the cosmic age of life. Most of the earlier potential lives died in blast zones before they could become anything we would recognize. Picture for a moment how the third type of blast catastrophe completes the trio. The third is the magnetar flare. Magnetars are neutron stars with extraordinarily strong magnetic fields, typically 1,000 times stronger than those of ordinary neutron stars and a quadrillion times stronger than Earth's magnetic field. Occasionally, a magnetar undergoes a giant flare, releasing a vast amount of energy in a fraction of a second. The flare emits gamma rays and X-rays in a broadly distributed pattern, less focused than a gamma-ray burst, but still capable of delivering significant doses to planets within roughly 10,000 light-years. A giant magnetar flare in 2004 from the magnetar SGR 1806-20 was detected on Earth as a brief but intense gamma-ray pulse. The pulse, which lasted less than 1/10 of a second, briefly heated and ionized the upper atmosphere. Had the magnetar been within a few hundred light-years instead of about 50,000 light-years away, the effects on Earth's biosphere could have been measurable. Magnetar flares are less frequent than supernovae or gamma-ray bursts, but they are not rare on cosmic timescales. Every habitable planet in the galaxy is potentially exposed to such events over its lifetime. The textbook does not anticipate that neutron stars, the dense remnants of dead stars, could be sterilization agents for living worlds across thousands of light-years. Few of us anticipate that the deepest gravitational graves of the cosmos are also the most distant killers. Nothing in the standard story anticipates how thoroughly the cosmos is filled with secondary executioners, each one a former star, each one capable of reaching out across enormous distances to end whatever biology had managed to survive the more ordinary slow killers. Mark this moment. The fourth graveyard is irregular in shape, scattered across the cosmos and dependent on chance geometry. Some planets, by accident of position, never face a serious blast event in their entire habitable lifetimes. Others are caught early and never get a chance to begin. The cosmic statistics are dominated by the fact that, on long time scales, every habitable planet faces some probability of catastrophic radiation exposure. The rate is low for any individual planet on any individual day. The rate is high enough, integrated over billions of years and across hundreds of billions of habitable candidates, to eliminate a substantial fraction. The numbers are difficult to pin down precisely. Different estimates give different fractions. Most serious work suggests that, across the history of the cosmos, between 10 and 50% of all otherwise viable habitable planets have been sterilized by blast zone events at some point in their lives. The blast zone graveyard contains hundreds of millions to billions of worlds in our galaxy alone. Across the observable universe, the count is in the trillions. Hold this image. The blast zone graveyard is the violent counterpart to the slow graveyards we have already visited. The frozen graveyard kills by neglect. The furnace graveyard kills by excess. The irradiated graveyard kills by relentless erosion. The blast zone graveyard kills by sudden cosmic accident. The four together account for nearly every category of natural environmental death that a planet can experience. The cosmos has many ways to end a world. Most worlds at some point encounter one of them. Tonight, we're going to look more closely at the Pliocene supernova story, because it is one of the most concrete pieces of evidence that the blast zone graveyard is not theoretical, but observationally real, and the evidence is in our own sediments. The first hint came in 1999, when a team led by Klaus Knie at the Technical University of Munich measured unusually elevated levels of iron-60 in a sample of deep ocean ferromanganese crust from the Pacific Ocean. Iron-60 is a radioactive isotope with a half-life of about 2.5 million years. It is produced in significant quantities only during the late stages of stellar evolution, particularly during core collapse supernovae. The presence of iron-60 in terrestrial sediments at concentrations above the normal background therefore suggests that the material was deposited from an extraterrestrial source, most likely the ejecta of a nearby supernova. Knie's initial detection was suggestive but not conclusive. The signal was weak, and the dating of the crust layers was imprecise. Follow-up work by his group and by independent teams over the next 2 decades refined the measurement and extended it to multiple sediment cores from different ocean basins. By 2016, the picture had become much clearer. Iron-60 deposits were detected in sediment cores from the Pacific, Atlantic, and Indian Oceans, in lunar regolith samples returned by Apollo missions, and in Antarctic snow cores. The deposits clustered in 2 distinct time windows, roughly 2 to 3 million years ago and roughly 6 to 9 million years ago. The 2 time windows correspond in cosmic terms to events in the recent geological past. 2 to 3 million years ago, hominins had already diverged from the common ancestor of chimpanzees and humans, and our own genus Homo was emerging in Africa. 6 to 9 million years ago, the great ape lineages were still in the process of separating. The iron-60 was being deposited on Earth at exactly the time when our distant ancestors were walking the African savanna. No one expects, when first hearing about cosmic radiation deposition, that the evidence would turn out to be visible in the same sediments that contain the fossils of our own evolutionary lineage. No one predicts that the geological record of recent supernova activity is, in a sense, layered alongside the geological record of human prehistory. Absolutely no one anticipates the way the cosmic blast zone graveyard becomes personal when you realize that 2 of the bursts touched Earth during the lifetimes of our own remote ancestors. The most detailed analysis of the iron-60 data, published by Anton Wallner and his collaborators in 2016, and again in 2020, suggested that the most recent event occurred approximately 2.5 million years ago, with the supernova exploding at a distance of roughly 300 light-years from Earth. The earlier event occurred approximately 6.5 million years ago at a slightly greater distance. Neither event was close enough to cause direct sterilization of Earth's biosphere. Both events were close enough to deliver measurable doses of radiation and to leave detectable chemical signatures in Earth's surface materials, pattern interrupt. The implications of these findings for the broader question of cosmic habitability are significant. Earth has been brushed by supernova ejecta multiple times in its recent history without suffering mass extinction. The radiation doses, while measurable, were not lethal. The atmospheric chemistry was perturbed but not catastrophically altered. Life continued. Our own lineage emerged into the era after the most recent event, but the safety margins were thinner than the surviving outcome might suggest. Had the supernovae been somewhat closer, say within 100 light-years instead of 300, the radiation doses would have been substantially higher. The ozone layer would have been significantly damaged. The ultraviolet flux at the surface would have spiked for years. The cosmic ray flux would have remained elevated for thousands of years. Some species, particularly those vulnerable to ultraviolet exposure, could have suffered population declines or local extinctions. Tonight, we're going to acknowledge the way Earth has, in this sense, been lucky in a measurable way. The supernovae that affected us were close enough to leave their fingerprints in our sediments, but not close enough to fundamentally damage our biosphere. Planets that happen to be located in star-forming regions of the galaxy, or near the centers of dense stellar clusters, would have experienced supernovae at substantially closer distances over their lifetimes. Some of those planets, by basic statistics, must have suffered events close enough to cause mass extinction or even complete sterilization. By the end of tonight, you're going to understand that the blast zone graveyard is not concentrated in any particular region of the galaxy, but the rate of deaths varies significantly with galactic environment. The galactic center, the spiral arms, and dense stellar clusters are riskier places for habitable planets than the quieter regions between arms. Earth's relatively safe position is, in this sense, part of the explanation for why our biosphere has survived for nearly 4 billion years without total interruption. The cosmic statistics, applied to planets in less fortunate positions, suggest that many billions of otherwise viable worlds across the Milky Way have been hit hard enough by nearby supernovae to lose their biospheres entirely. No one predicts, on a casual reading of cosmic statistics, that the galactic habitable zone would be as geographically structured as it turns out to be. No one expects that the question of whether a planet can host long-term complex life depends not just on the planet itself, but on its address within its galaxy. Absolutely no one anticipates the way galactic geography emerges as a critical filter for cosmic biology. The most recent additions to the Iron 60 story have come from a Wallner et al. Paper in 2021, which extended the measurements into Antarctic snow with extremely fine time resolution. The data suggest that Iron 60 is, in trace amounts, still being deposited on Earth in the present day, at rates consistent with the slow drift of ancient supernova ejecta through the local interstellar environment. The supernova that affected us are long gone, but their material continues to drift through our solar system, brushing past Earth and depositing micrograms of radioactive iron into our snow, our soil, our oceans. We are, in a literal sense, still receiving the slow mail from cosmic events that happened during the time of Australopithecus. The mail is harmless to us. The amounts are too small to affect anything, but the fact of the mail is itself remarkable. The cosmos sends us continuous low-level reminders of its violence, even when we are not paying attention. The blast zone graveyard is not just a distant catalogue of dead worlds. It is also a slow trickle of evidence raining down on our own surface, in amounts too small to harm but large enough to measure with the right instruments. What this leaves us with is one final graveyard, the strangest of all, the graveyard of civilizations. The fifth graveyard is the smallest, by raw count of worlds. It is also, by every meaningful measure of strangeness and weight, the largest. The fifth graveyard is the graveyard of civilizations. A small pause, because the entry point to this graveyard is the most uncertain ground we will cover all night. The previous four graveyards rest on direct astronomical evidence. We have seen the frozen surface of Mars. We have measured the runaway atmosphere of Venus. We have observed the flares of Proxima Centauri stripping the atmospheres of its planets. We have collected Iron 60 from nearby supernovae in our own ocean sediments. The first four graveyards are real in a way that does not depend on speculation. The fifth graveyard is different. It rests on no direct evidence. It rests on a question, the Fermi paradox, and on a framework, the great filter, that attempts to make sense of why the silence we observe in the cosmos is as deep as it is. The fifth graveyard is, in this sense, hypothesized rather than observed. but the hypothesis is taken seriously by many of the most thoughtful scientists working on questions of cosmic life today. The graveyard may not yet be visible. The reasons for thinking it exists are strong. Walk slowly with me through the basic argument. The Fermi paradox, named after Enrico Fermi, who reportedly asked the question over lunch in 1950 in the form, "So where is everybody?" runs like this. The galaxy is about 13 billion years old. The Sun is about 4.5 billion years old. There has been time in the galaxy's history for many generations of habitable planets to form. If even a small fraction of those planets developed life, and if even a small fraction of those lives developed intelligence, and if even a small fraction of those intelligences developed technology, then the number of technological civilizations in the galaxy's history should be in the millions or perhaps the billions. Even at modest expansion rates, well below the speed of light, a technological civilization could colonize an entire galaxy in a few tens of millions of years. The galaxy is hundreds of times older than this colonization timescale. Whether by colonization, by Bracewell probes, by Dyson-style stellar engineering, by megastructure construction, or simply by the accumulated radio noise of long-running technological societies, the galaxy should be full of visible evidence of civilization. The night sky should be lit with engineering. The radio spectrum should be loud with deliberate signals. The cosmos should be busy. It is not. The radio sky, after 70 years of careful listening, is silent. There are no Dyson swarms detected around any of the stars we have studied. There are no megastructures resolved in the imaging data. There are no laser pulses from interstellar communications networks. There are no probes in our solar system that we have been able to find. The cosmos appears, by every available measurement, to be empty of detectable intelligence. This is the paradox. The expected signature is loud. The observed signature is silent. Something has to give. Pause for a moment. The proposed resolutions of the Fermi paradox fall into several broad categories. Some say that intelligence is much rarer than the calculations suggest, because some step between simple chemistry and technological civilization is much harder than we assume. Others say that civilizations exist but are hidden from us, either deliberately or because they communicate in modes we cannot detect. Still, others say that civilizations exist but are too far away in space or time for their signals to reach us. And the most disquieting category says that civilizations do arise, often, and then end. They do not survive long enough to fill the galaxy with detectable engineering. They die. The disquieting answer has a name. The Great Filter, articulated most clearly in the late 1990s by Robin Hanson, is the hypothesis that there exists, somewhere along the path from simple chemistry to long-lived galactic civilization, a step that is much harder than the others, a step that eliminates almost all candidates, a step that, on every world that begins the path, almost always ends the path before completion. The Great Filter could be in many places. It could be the origin of life itself, in which case the cosmos contains many sterile worlds and very few living ones. It could be the development of complex cells, the leap from single-celled to multicellular life, the development of nervous systems, or the rise of technological intelligence. It could be a step that we have already passed, in which case our long survival from here is more plausible, or it could be ahead of us, in which case our long survival is much less plausible. The standard intuition does not predict which version is correct. We have only one example of life arising, our own planets. We have only one example of complex multicellularity, intelligence, and technological civilization. We cannot, from a single data point, say which step was the hardest. We can only say that, given the silence of the cosmos, at least one step must be very hard. The Great Filter exists somewhere. The question is whether we have already passed it or whether it lies ahead. Settle in here. If the Great Filter lies ahead of us, then the graveyard of civilizations is, in some sense, our likely future. The implication is that almost every civilization that ever rose in cosmic history reached a stage roughly comparable to ours, and then, by some mechanism we have not yet identified, did not survive past it. The mechanism could be self-destruction through nuclear war or biotechnology. It could be ecological collapse through atmospheric or climate change. It could be a particularly subtle problem we have not yet recognized, perhaps related to the nature of artificial intelligence or the trajectory of technological development itself. The shape of the graveyard of civilizations in this picture is unsettling. It is composed of worlds that, for tens of millions of years or hundreds of millions of years, were quiet and biological. Then, in geologically brief windows of perhaps a few thousand to a few 100,000 years, they developed cities, technology, science, and possibly the capacity for interstellar communication. Then, within a few thousand years of reaching that capacity, they ended. The surface fell silent. The radio signals stopped. The cities decayed. The technological signatures, if any survived for centuries afterwards, faded into the cosmic background. If you sat with a telescope at a million-year time resolution and watched a galaxy like the Milky Way over the past few billion years, you might see, scattered across the disk, brief flashes of technological activity, a burst of radio noise in one place, a few thousand years later, another burst in another place, most of the bursts winking out within a few thousand years of their first appearance, most of the civilizations briefly visible and then silent. The cosmic graveyard of civilizations in this model is not a pile of bodies. It is a pile of brief lights, worlds where, for a moment, intelligence ran the surface, asked questions about its own existence, and then ceased. Notice that this picture has both a melancholy and a strange consolation to it. The melancholy is obvious. The consolation, if it is consolation, is that the universe is not indifferent. It is in fact a long sequence of attempts. Every attempt that has been quiet for thousands of years was, at one point, a civilization that looked up at its own sky, asked the same questions we are asking, and tried to make sense of its own existence. Their telescopes pointed in many directions. Their voices went out into the dark. They were our predecessors in a sense, even though we will never directly know any of them. For the next stretch, we consider what specific shape the great filter might take, because the shape matters for thinking about our own position in the picture. There are several candidate filters that have been seriously discussed. The first candidate filter is the origin of life. If abiogenesis, the chemical transition from non-living matter to self-replicating biology, is intrinsically very difficult, then the filter is behind us. The universe contains many sterile worlds, very few worlds with even simple life, and ours is one of the rare ones that succeeded at the hardest step. This is in some ways the most hopeful version of the great filter, because it implies that the difficulty is past and the future is open. The second candidate filter is the development of complex life. Even if abiogenesis is common, the transition from single-celled life to multi-celled life took on Earth roughly 2 billion years after life first appeared. This is a significant fraction of cosmic time. If this transition is similarly difficult on most worlds, then the cosmos may contain many bacterial worlds and very few worlds with anything more complex. Earth would, again, be among the rare survivors of a difficult step. The third candidate filter is the development of technological intelligence. The Earth has hosted complex multicellular life for about 600 million years. It has hosted vertebrate animals for about 500 million years. It has hosted humans for only a few 100,000 years, and technological civilization for only a few thousand. The transition from complex animal to technological civilization happened, on Earth, very recently and very quickly. If this transition is also rare or difficult, the filter may be located here, and we may be among the rare worlds that have crossed it. The fourth candidate filter is the most disquieting. It is the survival of technological civilizations past their first few thousand years. If almost every civilization that develops technology also develops, Simultaneously, the capacity to destroy itself through nuclear weapons, biotechnology, climate disruption, or some other mechanism, then most civilizations end shortly after they begin. The filter in this picture is ahead of us. We are right at it. Our long-term survival depends on solving problems that, by the Fermi argument, almost no previous civilization has solved. A slow turn. Sit with this. The fourth candidate filter is not the only possibility, but it is consistent with the observed silence. If the cosmos is full of dead worlds because civilizations consistently end themselves shortly after they begin, then the graveyard of civilizations is the largest single category in this fifth graveyard. It is a graveyard of brief, bright, self-extinguishing lights. There is another consideration that does not fit neatly into the great filter framework, and it is worth marking. Even civilizations that do not self-destruct may, after some time, simply lose the will to broadcast. They may turn inward, focused on internal questions rather than external expansion. They may communicate at frequencies or in modes that we cannot detect with our current technology. They may exist in the cosmos right now, but be silent in the way that a human meditator can be silent without being absent. The fifth graveyard, in this picture, contains some worlds that are not dead at all, but simply quiet. The distinction matters philosophically. It also matters for how we might one day search for them. The most recent serious attempts to estimate the cosmic civilization census, including work by Anders Sandberg and Eric Drexler at the Future of Humanity Institute, have shown that the uncertainties on the parameters in the Drake equation are wide enough that the expected number of civilizations in the observable universe ranges from less than 1 to more than a quintillion. The range is so wide that no single answer can be defended. The most probable answer in the Sandberg analysis is that the cosmos contains relatively few active civilizations at any given moment. Either life is rare, or civilizations are short-lived, or both. The implication, either way, is that the graveyard of civilizations contains either very few worlds or very many. The expected total, integrated over cosmic history, is probably in the range of millions to billions, but the wide uncertainty makes any specific number hazardous. What this picture tells us is that the fifth graveyard is the most speculative of all, and also the most personal. We are ourselves a civilization that has been technologically active for only a few thousand years. We may be near the beginning of a long, stable trajectory. We may be near the end of a brief, ordinary one. The cosmic statistics taken at face value do not strongly favour either possibility. Step back and you can see that the constellation, again, is in the sequence. Every civilization that ended was, at some point, alive. Every world that fell silent was at some point asking questions. The cosmos has produced this kind of activity many times. It will presumably produce it many more times. We are part of a long sequence, of which we cannot see the earlier members and may not see the later ones. Our place in the sequence is the present moment. Our task, if we have one, is to live as well as we can in our own brief window, knowing that we are not the first to do so, and probably not the last. Tonight, we're going to walk through the Drake equation in detail, because the equation is the framework through which the size of the fifth graveyard has been seriously estimated for 60 years, and the parameters of the equation tell a quiet story of their own. The Drake equation was first proposed by Frank Drake in 1961, at a small meeting at the Green Bank Observatory in West Virginia that became known as the first SETI conference. Drake was trying to organize the discussion about how many communicating civilizations might exist in the Milky Way. He wrote down a multiplicative equation containing 7 factors. The number of communicating civilizations equals the rate of star formation in the galaxy, times the fraction of stars with planets, times the fraction of those planets that are habitable, times the fraction of habitable planets where life actually arises, times the fraction of those where intelligence evolves, times the fraction of intelligent species that develop the technology to communicate, times the average lifetime of such civilizations. Each factor has its own uncertainties. The earlier factors dealing with stars and planets have become much better constrained in the 60 years since the equation was written. The later factors, dealing with intelligence and civilization lifetimes, remain almost entirely unknown. The star formation rate in the Milky Way is now known to be about 1 to 3 solar masses per year, integrated over the disk. The fraction of stars with planets is now known, from Kepler and TESS, to be high, probably more than half. The fraction of stars with planets in the habitable zone is now estimated at perhaps 10 to 20%. The fraction of habitable zone planets that are actually habitable, in the refined sense we discussed earlier, is probably lower, perhaps 1 to 10%. The fraction where life arises is unknown. The fraction where intelligence evolves is unknown. The fraction that develops communicative technology is unknown. The average lifetime of such civilizations is unknown. No one expects, when first encountering the equation, that more than half of its parameters would remain almost entirely unconstrained even after 6 decades of work. No one predicts that the equation would prove most useful as a structured way to articulate our ignorance, rather than as a tool for calculating numbers. Absolutely no one anticipates that the most important factor in determining the size of the cosmic civilization graveyard is one of the most uncertain, the average lifetime, pattern interrupt. The civilization lifetime parameter, denoted as L in the standard notation, has a particularly disquieting role in the equation. If L is large, perhaps millions of years or more, then the galaxy should contain many communicating civilizations at any given moment, even if all the other factors are modest. If L is small, perhaps only a few thousand years, then most civilizations that have arisen in cosmic history have already ended, and the number currently active at any moment is tiny. The Fermi paradox in some interpretations is just an empirical constraint on L. The silence we observe is consistent with L being small. By the end of tonight, you're going to understand that the fifth graveyard's size depends most sensitively on this single parameter. If L is 1 billion years, the galaxy contains tens of thousands of active civilizations, and the cosmic graveyard of past civilizations is in the millions. If L is 1 million years, the galaxy contains a few dozen active civilizations, and the graveyard contains a few hundred. If L is 1,000 years, the galaxy contains essentially 0 active civilizations at this moment, and the graveyard contains perhaps tens of millions of past civilizations whose remains have been mostly buried by cosmic time. The empirical evidence, in the form of the Fermi silence, is consistent with L being on the shorter end of the plausible range. We do not see active civilizations. We do not see their signals. We do not see their engineering. The simplest explanation, by Occam's razor, is that they are not there to be seen because they ended a long time ago. Tonight, we should also acknowledge the categories of signals SETI programs have been looking for, because the absence of detection across all of these categories sharpens the puzzle considerably. The first category is narrowband radio signals. SETI's original strategy, dating to Frank Drake's 1960 Project Ozma, has been to search for radio signals at specific narrow frequencies that would indicate a deliberate technological source rather than natural astrophysical emission. Decades of searches, including the Allen Telescope Array, the Breakthrough Listen project, and various international collaborations, have monitored thousands of stars and hundreds of frequencies. The total number of star frequency combinations searched is enormous. The number of confirmed extraterrestrial signals is 0. The second category is optical and infrared signals. Laser pulses, if used for interstellar communication, would be detectable across substantial distances. Searches with dedicated optical SETI instruments have looked for nanosecond-scale flashes from nearby stars. None have been confirmed. JWST and other infrared facilities have searched for thermal anomalies that might indicate Dyson swarms or other megastructures. None have been confirmed. The third category is technosignatures. Beyond direct communications, technologically advanced civilizations might leave indirect signatures in their stellar systems. unusual chemical compositions in atmospheres, including artificial pollutants, anomalous transit signatures that could indicate megastructures, excess infrared emission consistent with stellar engineering. Searches for these signatures, including dedicated analyses of Kepler data and ongoing work with TESS, have found a few intriguing candidates but no confirmed technosignatures. The fourth category is direct visitation, the possibility that a sufficiently advanced civilization could send probes to our solar system has been discussed seriously for decades. Searches for artificial objects in unusual orbits, including the dedicated study of interstellar visitors like Oumuamua and Borisov, have not produced confirmed evidence of artificial origin. Most analyses interpret these objects as natural interstellar bodies, though some researchers, including Avi Loeb at Harvard, have argued for considering artificial origin hypotheses more seriously. No one expects, after 70 years of searches, that every category would come up empty. No one predicts that the cosmic silence would prove this robust across radio, optical, infrared, and direct visitation searches. Absolutely no one anticipates the way the silence becomes more meaningful as more categories are checked. By the end of tonight, you're going to understand that the silence is not a casual absence of evidence. It is, increasingly, a systematic absence across multiple independent observational categories. The fifth graveyard, the graveyard of civilizations, is consistent with this silence in a way that almost no alternative resolution of the Fermi paradox is. The civilizations may have existed. They may have left signatures. The signatures have not reached us, or the civilizations did not last long enough to produce signatures that reached us, or both. Tonight, we should sit with one final consideration about the fifth graveyard. The civilizations that ended did not, in most plausible scenarios, end suddenly. They likely ended through processes that the civilizations themselves could see coming, perhaps for decades or centuries. Climate failure, resource exhaustion, internal conflict, the consequences of poorly managed technologies. The endings, if our own current trajectory is informative, are slow rather than sudden. The cosmic graveyard of civilizations is therefore in some sense a graveyard of long quiet deaths, in which the inhabitants knew what was happening and continued to live their lives anyway. Hold the image. Each civilization that ended likely had its own version of this exact moment. Someone sitting quietly at night, listening to a description of cosmic threats, trying to make sense of why so many other worlds had ended. Each civilization had its own scientists, its own poets, its own children, its own evenings. Each one ended. The cosmos contains the records of all those endings, written in the silence of radio bands that should be loud and are not. The graveyard is not just statistical, it is composed of moments. Every moment in it was at one point lived. Hold the thought. 5 graveyards, each one real in different ways, each one full in different degrees. Together they account for the cosmic absence we measure when we look at the radio sky and find it silent. Together, they explain why the universe, despite being old enough and large enough to host vast amounts of intelligence, appears to host only the kind of intelligence that exists for a brief moment and then is gone. By the end of tonight, you will have walked through every category of cosmic death that current science recognizes. You will know what kills planets, and what kills oceans, and what kills atmospheres, and what kills civilizations. You will know, in a quiet and unhurried way, that the universe is full of endings as well as beginnings. And you will know that this is not a reason for despair. It is, in some way that is hard to articulate but easy to feel, a reason for gentleness. Now, the final return to the small lit room where you are sitting. The cosmos is what it is. The graveyards are what they are. The night is here. The story can rest. Tonight we're going to step back from the 5 graveyards and ask a question that frames all of them at once. When, in cosmic history, did the universe become quiet enough to allow life to begin in earnest? Because the timing matters. The graveyards we have just walked through are not evenly distributed across cosmic time, they cluster. Before we get started on the chronology, sit with the basic shape of cosmic history. The universe is about 13.8 billion years old. The first stars formed within the first few 100 million years. The first heavy elements, the carbon and oxygen and iron that biology requires, were forged in those first stars and scattered into the interstellar medium when those stars died. The first rocky planets, capable of hosting biology in principle, did not form until the heavy element abundance reached a sufficient threshold, perhaps 1 billion years after the Big Bang. The first habitable worlds, therefore, are no older than about 12 billion years. Now, let's begin to think about what those first 12 billion years actually looked like for any potential biosphere. The early universe for the first several billion years was a violent place. The galactic disks were younger and more compact. The supernova rates were higher. The gamma-ray burst rates were dramatically higher, perhaps 100 times the present-day rate at the peak of the cosmic dawn. The cosmic ray background was higher. The radiation environment that any early habitable planet had to endure was, on average, far more hostile than the environment that planets enjoy today. No one expects, on first thinking about cosmic history, that the conditions for biology have actually become friendlier with time. No one predicts that the universe of the present moment is genuinely calmer than the universe of 10 billion years ago. Absolutely no one anticipates that we may be alive at the start of a cosmic era that is, by historical standards, unprecedentedly quiet. Expectation. The universe has always been roughly the same kind of place, with biology arising and dying at roughly steady rates throughout cosmic history. Reality. The universe has slowly become safer for biology as the dense early epochs gave way to the spread-out present epoch, and we may be alive in the first window when sustained biological evolution has been broadly possible across a substantial fraction of galactic real estate. Pattern interrupt. Sit with this. The cosmic dawn era was loud with gamma-ray bursts, dense with supernovae, and dominated by short-lived massive stars whose lifetimes were too brief to allow stable biological evolution. The first stable habitable epochs may not have begun until perhaps 8 or 9 billion years after the Big Bang. Earth, having formed roughly 9 billion years after the Big Bang, may have been among the first planets in cosmic history to enjoy the new quiet. We may, in a meaningful sense, be among the earliest waves of biospheres that the cosmos has ever permitted to develop continuously. By the end of tonight, you're going to understand that this changes the cosmic graveyard picture significantly. The first 4 graveyards we walk through, the frozen, the furnace, the irradiated, and the blast zone, were all filled throughout cosmic history, with the rates varying as the cosmic environment changed. The 5th graveyard, the graveyard of civilizations, is much younger. It cannot contain civilizations older than the universe permitted them to exist. If sustained biological evolution only became broadly possible 4 or 5 billion years ago, then the oldest civilizations in cosmic history are no older than perhaps a few billion years. The graveyard of civilizations is therefore relatively young, in cosmic terms. Tonight we're going to consider what this implies for our position in the sequence. If we're alive during one of the earliest sustained biology epochs in cosmic history, then we are not late, as the simple Fermi argument suggests. We are early. The cosmos may, in this picture, become much busier with civilizations over the next 10 to 100 billion years, as the cosmic dawn fades further into the past, and the conditions for biological continuity become even more favourable. No one expects, on first reading about the Fermi paradox, that the resolution might be that we are too early rather than too late. No one predicts that the loud cosmos of the deep past might explain the silent cosmos of the present. Absolutely no one anticipates that the timing of cosmic biology, integrated across the full age of the universe, places us not at the end of a sequence, but near its beginning. Before we get started on the full implications, sit for a moment with how strange this reversal of expectation is. The standard Fermi reading is that we are alone because earlier civilizations had time to fill the galaxy, and apparently did not. The cosmic timing reading is that we're alone because the conditions for sustained civilization only recently became available, and most other civilizations have not yet had the time to arise. The two readings produce identical observations, a silent radio sky, but they point in opposite directions about the future. Expectation. The cosmos is full of dead civilizations because intelligence is short-lived. The textbook says, "We are late," and the others have already ended. The cosmic timing reading. The cosmos is mostly silent because intelligence is just now beginning to be possible, and most of the others have not yet arisen. Few of us anticipate that both readings could be partially correct. The cosmos may contain both ancient civilizations that ended and new civilizations that are just beginning, with the present moment sitting somewhere in the middle of the transition from a sterile early universe to a busier future one. Earth's biosphere in this picture is among the first waves of a cosmic biological era that will eventually become more populated. Now, let's begin to fold this insight back into the graveyard structure. The frozen graveyard is full and has been full for cosmic ages. The furnace graveyard is full and has been full for cosmic ages. The irradiated graveyard is full and has been full for cosmic ages. The blast zone graveyard is full, but was more deadly in the past than it is now. The fifth graveyard, the civilizations, is a smaller graveyard than the others, but it is growing slowly as each new civilization that arises eventually ends. The size of the fifth graveyard depends entirely on how long civilizations typically last. If they typically last a few thousand years, the graveyard has been filling rapidly for the past few billion years. If they typically last millions of years, the graveyard is small, but the active civilization count is correspondingly larger. Pattern interrupt. The most honest assessment based on everything we have discussed tonight is that we genuinely do not know which scenario is correct. We have one data point, our own. Our civilization has been technologically active for a few thousand years. Whether we last for 10,000 more years or 10 million more is not knowable from the inside. We can hope, we can work, we cannot, with current understanding, predict. By the end of tonight, you're going to understand that this is not a failure of our science, but a feature of our position. We are a single sample in a vast distribution. Statistical inference from a single sample is severely limited. The graveyard of civilizations is, in this sense, an empirical question that we cannot yet answer from inside our own civilization. The answer will become clearer as future generations gather more information, perhaps by detecting other civilizations, perhaps by surviving long enough to fill in their own civilization lifetime parameter, perhaps simply by learning more about the deep history of biological emergence in cosmic systems. Tonight, we're going to acknowledge that the timing question reframes the entire emotional tone of the cosmic graveyard. If we are late, the graveyards represent loss. If we are early, the graveyards represent prologue. Both readings respect the data. Both readings acknowledge the silence. The difference is which direction the silence points, backward toward extinguished histories or forward toward unwritten futures. No one predicts, after sitting with this for a moment, that the answer to whether the cosmic graveyard is melancholy or hopeful depends so sensitively on our position in cosmic time. No one expects that the same observation, an empty radio sky, can be read in such radically different ways depending on a single chronological assumption. Absolutely no one anticipates the way the question of cosmic timing becomes the most important philosophical question we can ask about our place in the universe. Before we get started on the final reflection, take one more moment with the chronology. The cosmos will, in all likelihood, continue to exist in something resembling its current form for at least the next 100 billion years before the slow heat death begins to dominate. That is more than 7 times the current age of the universe. The era of sustained biological possibility on cosmic scales has barely begun. If life is as common as the planet count suggest, and if civilizations rise as readily as the chemistry suggests, then the cosmos will see, in its long future, far more civilizations than it has yet produced. The graveyard of civilizations will grow. It will also presumably be matched by a corresponding growing population of living civilizations. The balance between active and ended biospheres is not fixed. It is, on cosmic timescales, in motion. The takeaway is that the cosmic graveyard, all 5 of its categories combined, is not a complete catalogue of cosmic biology. It is a snapshot of biology as it currently stands, in the present moment, in this specific cosmic era. The catalogue will change. The future cosmos will produce many more entries on both sides of the ledger, the alive and the dead. We are sitting at one frame of a film that has been running for a long time and will run for much longer. Take a moment to add one final layer to the picture before the long walk back to your own room. The graveyards we have walked through are not the whole story. There is a parallel cosmos of worlds that by chance or by chemistry have done better than the median. Earth is one of them. Earth has survived 4.5 billion years of cosmic environmental risk without total interruption. Earth has, in this run, dodged the inner edge of the habitable zone, the outer edge, the great supernova close passes, the gamma-ray bursts that might have come and did not, and so far the great civilization-ending filter that the Fermi argument so quietly threatens. Earth is, in a real and specific sense, one of the survivors. No one expects, on first walking through the cosmic graveyard, that the most useful thing to do with a picture is to feel grateful rather than mournful. No one predicts that the proper response to the great quiet is reverence rather than fear. Absolutely no one anticipates the way the size of the graveyard makes the small lit shelves of life that remain feel precious rather than fragile. Pattern break. The cosmos is large enough that everything possible has happened somewhere. The cosmos is patient enough that everything possible will happen again. The cosmos is generous enough that, on any given night, in any given quiet room on any given surviving world, a single person can hold the whole story in mind for a few hours and then fall asleep. By the end of tonight, you're going to understand that the graveyard is not the moral of the story. The moral of the story is the survival. The graveyard is the backdrop against which survival becomes legible. Without all those dead worlds, the cosmos would not need an Earth. The presence of Earth is, in a strange way, the answer to the silence of the others. The cosmos is making attempts. Most of them end. Some of them continue. We are tonight one of the continuing ones. Now, let's begin the slow descent back to the room you started in. The cosmos can wait. The graveyards will keep. The night is doing its quiet work all around you, and there is nothing left to do tonight except let the picture settle and the breathing slow. For a long stretch of cosmic history, you would have been the only one looking up. Allow me a final image. The Milky Way, seen from a distance of 100,000 light-years, is a faint glowing disk, an island of stars in an enormous quiet. Across that disk, scattered through its arms and its bulge, sit perhaps 100 billion stars. Around a third of those stars host planets. A small fraction of those planets ever held conditions friendly to life. A smaller fraction still ever produced biology. A smaller fraction again ever produced minds. A smaller fraction still ever produced civilizations. And of those civilizations in the picture we have walked through tonight, almost all are gone. The disk is full of quiet places. The light from those places is the light of stars that never knew. The planets they were warming were once busy with attempts at thought. Picture this slowly. The camera in your imagination drifts in from intergalactic distance. The disk grows. The arms become visible. Individual stars resolve. The blue and red and yellow points of light each have their own histories, their own planetary systems, their own former biospheres perhaps, that we will never directly know about. Some of those points are graves. Some are quiet basements with hidden oceans. Some are baked rock, some are stripped rock. Some, perhaps, hold the last few cities of a civilization in its final centuries, broadcasting nothing, watching its sky as we watch ours. The camera drifts closer. It finds a particular star, an ordinary yellow main sequence dwarf, about halfway out from the center of the galaxy, in a quiet region between two spiral arms. Around that star, a small family of rocky and gas planets. The third rock from this particular star is blue and white, with cloud patterns moving slowly across its surface. On the night side of that planet, lights. The lights are not random. They're arranged in the patterns of cities and roads and farms. A civilization in this moment of cosmic time is alive on that surface. The camera drifts closer still. It finds a single building. Within the building, a room. Within the room, a quiet bed. On the bed, a single person, listening to a voice describe the cosmic graveyard from which their own world has, for the moment, been spared. Let the camera rest there. The cosmos is large. The cosmos is old. The cosmos is full of endings that no one alive today saw arrive. And yet, here you are, on this particular night, on this particular planet, in this particular room, listening to a voice describe a great and quiet cemetery that you are not, yet, a part of. There is no need to be afraid. The endings are real, but they are also old. Most of them happened millions or billions of years ago. The light from them is just now reaching you. You're not being asked to feel grief for them. You're being asked to feel companionship with them. You're part of the same long sequence that produced them. Their absence is the texture of the cosmos in which your presence makes sense. The sky overhead, on a clear night, holds the light of stars whose planets, in many cases, are graves. The cosmic background radiation, the leftover glow of the early universe, holds the imprint of a time before any planet had ever cooled enough to be a candidate for life. The entire visible cosmos is a record of beginnings and endings, layered on top of each other, drifting outward from a hot common origin. You sit at the present moment, with the past all around you and the future yet to be written, and the only really sensible thing to do tonight is to let it all pass through you slowly, without trying to hold any of it. If the cosmos is full of dead worlds, then your alive world is precious, not because it is special, not because it is the only one, but because, of all the possible configurations of matter and energy and time, this one, this particular one, this single small blue planet you happen to be living on, is the one whose air you are breathing, whose surface you're touching, whose history you are part of. The other worlds have their stories, and they will have other listeners if anyone is left to listen. This world has you. A quiet pause. Let the room settle. The graveyards are out there, but they're not in here. In here, the air moves. In here, the heart beats. In here, the mind, for whatever brief or long stretch it has, gets to look at the cosmos and ask what it is. That asking is, in the most literal sense, the cosmos becoming aware of itself, briefly, through the small window of your particular consciousness. The window will close at some point, as all windows do. But while it is open, you can look. The cosmos has produced this exact moment, with you in it, by a chain of accidents and necessities that includes the death of every other world we have walked through tonight. The Mars that died gave Earth its quiet neighborhood. The Venus that ran away gave Earth a slim margin. The supernovae that came close enough to leave iron-60 in our ocean sediments also enriched the early solar system with the heavy elements your body is made of. The cosmos is not separated from you. The cosmos is the long and patient process that arrived, eventually, at the room you are in. Sleep can come whenever it wants now. The story has done its work. The graveyards are mapped. The picture is whole. The night is yours. Sleep well tonight, and tomorrow we will continue to explore the deepest mysteries of the cosmos together.